In the silence between galaxies, a shadow stirs, a force so deep it bends the breath of time. Beneath a neutron star's cracked iron skin, a single spoonful outweighs the tallest mountain's climb. Within the black hole's silent scream, gravity devours even law and light. But power is not always fury. Sometimes it glows or vanishes or dreams in night. One flare of light can end a world. One trembling chance can birth them all. The universe bows not to kings, but to this unseen call. Prepare for a journey through power beyond comprehension. We begin. It begins not in silence, but in pressure, ancient, patient pressure. Deep in the heart of a massive star, fusion rages like a furnace god, forging heavier and heavier elements from the breath of hydrogen. For millions of years, the star burns brighter than anything around it, held in perfect balance, gravity pulling inward, fusion pushing out. But all balance must one day break. Iron is the final breath. When the star begins to produce iron in its core, the dance ends. Iron does not give energy when fused, it only takes. And so, in a single moment, the outward push fails. Gravity, no longer opposed, collapses the core with unimaginable violence. What happens next is not just an explosion, it is the explosion. A supernova erupts, the most powerful single event known in the modern cosmos. In the span of seconds, the collapsing core rebounds and a shockwave tears through the star's outer layers. The heat reaches hundreds of billions of degrees. Neutrinos, ghostly, nearly massless particles, flood the universe in numbers beyond counting. For a brief instant, this single star outshines an entire galaxy. And then comes the ash of power: gold, platinum, uranium, the heavy elements that fill our bones, power our circuits, and glint from our rings. We are not made from the stars, we are made from their deaths. A scientific truth: a Type II supernova can release 10^44 joules of energy, more than the sun will emit across its 10 billion year life, a trillion atomic bombs, all at once. That is the weight of a dying star. Yet even in such staggering output, questions remain. How precisely does the core collapse? What triggers the rebound? We model it, simulate it, theorize it, but the heart of the explosion is still shrouded, hidden behind light years and layers of iron, plasma, and time. The internal physics of a star's death remain one of astrophysics' unsolved mysteries. But speculation, too, has power. Some believe that in the moment just before collapse, something stranger might occur, that the core could momentarily form a quark-gluon plasma, a state of matter where particles cease to exist as individuals and become a sea of pure, strong force. Others suggest a link to dark matter, that something invisible may catalyze collapse or distort the process in ways we cannot yet see. And perhaps even more mysterious is what comes after. For sometimes what is left behind is not dust, but a neutron star, or worse, a black hole. The energy of death does not end. It transforms. It compresses into something smaller, denser, and even more dangerous. To grasp this, picture this. A star with the mass of 20 suns collapses into a sphere no wider than a city. Imagine a mountain crushed into a teacup. Now imagine the pressure that holds it there. The light from that supernova may still be traveling, long after the star itself has vanished. In fact, some of the light you see in the night sky tonight, faint pinpricks in the dark, may be ghosts from such cosmic funerals, still racing across the universe to reach you. In the blink of a star's death, we glimpse power unbound. But death is not the end, it is a door. The collapse leads us somewhere deeper, into regions where gravity no longer behaves, where even time may fray. And so we follow the trail of force inward, toward a place from which nothing can return. At the edge of a dying star's collapse, a line is crossed, a threshold so final that even light cannot escape. Gravity, no longer satisfied with crushing matter, begins to consume the very rules that once contained it. This is no longer a place in space. It is the absence of place itself. A black hole is not a thing. It is a boundary, a hunger, a silence that has weight. Imagine a sphere the size of a city, yet containing the mass of several suns. And now imagine that nothing, no photon, no signal, no hope, can escape once it crosses the event horizon, the invisible shell that seals this object from the rest of reality. From the outside, the black hole appears frozen in time, a dark orb, lightless and silent. But from within, time does not just slow, it shatters. Einstein's general relativity predicted them, though even he doubted their reality. Now, we know they exist, not just in math, but in motion. The LIGO Observatory has heard their collisions in the form of gravitational waves, ripples in the very fabric of space-time. Telescopes have seen their silhouettes cast against fields of stars. And yet for all this observation, the inside remains unknowable. A scientific fact. When mass collapses beyond a certain density, it forms a singularity, a point of infinite curvature, where the known laws of physics break down completely. Infinities are the universe's way of saying, you do not understand this yet. Black holes are not merely prisons of light, they are creators of paradox. One such enigma is the information paradox, a question raised by Stephen Hawking that still unsettles physics. If nothing escapes a black hole, what happens to the information about what fell in? Quantum mechanics insists that information cannot be destroyed, but general relativity cares nothing for such rules. The two most successful theories of modern physics collapse into contradictions at the black hole's edge. Here, at this intersection of mass and mystery, speculation blooms. Some suggest that black holes are not endpoints but gateways, perhaps to other universes, through theoretical tunnels called wormholes. Others propose that the singularity does not truly exist, that quantum gravity, a theory not yet found, will resolve the infinity into something real, measurable, and strange. And then there is the question of what happens if you fall in. You would not feel pain at first. The pull of gravity would differ across your body, your feet dragged faster than your head. This stretching, called spaghettification, is not poetic exaggeration. It is a calculated effect of tidal gravitational forces. In the final seconds before you cross the horizon, an outside observer would see you freeze, red-shifted into invisibility, but from your perspective you fall freely, and perhaps you fall forever. There is a haunting beauty in the idea that the most powerful thing in the universe may be invisible, not because it is small, but because it bends space until light itself cannot carry its image. Yet even the mighty may fade. Black holes, once thought eternal, may slowly evaporate through Hawking radiation, a quantum leakage caused by particle-antiparticle pairs near the event horizon. Over time, scales longer than galaxies exist, even black holes may vanish. What remains? We don't know. Perhaps only information scattered through faint final radiation, perhaps a remnant, or perhaps a truth we've yet to imagine. But if black holes are gravity's crescendo, they are not its beginning. There is a deeper force, one that resists gravity itself. It does not tear the universe apart, it holds it together. We turn inward now to the smallest scales imaginable, to the glue of the atom, to the strong force. Dive now beneath the skin of matter, past molecules, past atoms, past electrons and orbitals, into the nucleus where protons and neutrons cluster like heavy stones in a tiny temple of energy. And even here, smaller still, lie quarks, the tiniest known shards of existence. But what binds them together? What stops the positively charged protons from exploding apart? By all logic, they should repel each other, furiously, violently, and yet they do not. Something stronger than repulsion holds them in place. This is the strong nuclear force, the most powerful of all the four fundamental forces. It is not obvious like gravity. It does not light up the sky like electromagnetism. It hides quietly inside the heart of everything, keeping matter whole. It is a force of incredible reach, but only over incredibly short distances. Move two quarks slightly apart, and the force snaps tighter, like a cosmic rubber band. Pull hard enough, and something astonishing happens. The energy used to separate them doesn't free them. It creates new quarks instead. The strong force does not like solitude. It would rather split itself into new particles than let one drift alone. This phenomenon is called color confinement, a poetic name for a brutal truth. Quarks are never found alone in nature. They are bound forever in groups, sealed by the strong force's unbreakable grip. It is the closest thing to an absolute prison in the physical world. A scientific fact, the strong force is about 100 times stronger than electromagnetism, and many orders of magnitude stronger than gravity. If gravity pulls, the strong force welds, and yet we do not fully understand its inner mechanics. The theory that describes it, quantum chromodynamics or QCD, is elegant in mathematics but nearly impossible to calculate at scale. It involves gluons, the exchange particles that glue quarks together constantly. But power does not only cling, it can also repel, push, accelerate. There is a force spreading the universe apart, not like an explosion, but like the swelling of space itself. From the nucleus, we leap outward now, toward the expanding void, toward dark energy. Look up, and you see a night sky dotted with stars. Some faint, some bright, most already dead. But between them lies a greater mystery, space itself. And space is not still. It expands, it grows. Every second, every year, every cosmic breath, the distance between galaxies stretches. Not because the galaxies are moving through space, but because space is making more of itself. This discovery was a shock. When Edwin Hubble first observed that galaxies are racing away from us, scientists believed the universe must be slowing down, gravity pulling back on its own expansion. But in 1998, twin teams observing distant supernovae found something no one expected. The expansion isn't slowing. It's speeding up. Something everywhere and nowhere is pushing the universe apart, gently, steadily, unstoppably. We call it dark energy. We do not know what it is. It makes up roughly 70% of the universe, yet it cannot be touched, seen, or measured directly. It does not clump like matter, nor warp space like gravity, and still, it shapes the cosmos on the grandest scales. A scientific fact, dark energy causes the expansion of space to accelerate. It is not a force between objects, it is a property of the vacuum. As more space appears, more dark energy appears with it, an endless, self-sustaining swell. Some physicists model it as a cosmological constant, a fixed energy density embedded in the vacuum, a number plugged into Einstein's equations. Others imagine it as a dynamic field, quintessence perhaps, an evolving energy that changes with time. But no one knows, and stranger still, why now? The universe has existed for nearly 14 billion years. For most of that time, gravity dominated, and the expansion slowed. Only recently, cosmically speaking, has dark energy begun to accelerate it. Why did this transition happen now, just as intelligent observers like us appear? This puzzle is called the cosmic coincidence problem, and it haunts cosmology like a riddle whispered across time. Speculative theories bloom in its shadow. Some suggest that dark energy is not constant, that it will decay, perhaps violently, triggering a phase transition that rewrites the laws of physics. Others propose the Big Rip, a future where dark energy grows stronger and stronger, tearing apart galaxies, stars, planets, even atoms, until space itself shreds into discontinuity. Or perhaps we misunderstand it entirely. Perhaps dark energy is not a thing, but a sign that our theories of gravity are incomplete on large scales. Modified gravity, extra dimensions, or emergent space-time, all are ideas on the table. Still, the effect is undeniable. Galaxies once drawn together now drift away. The great clusters thin. The night sky dims. And in the far future, hundreds of billions of years from now, observers may see nothing but darkness. The visible universe shrinking to silence. The stars gone. The signals lost. Power here is quiet. It does not burn. It does not crush. It simply expands, patient and invisible. And in that expansion, it overcomes everything. But power can also be subtle, layered, and strange. Beneath the great forces and the visible cosmos, a deeper framework hums, fields that ripple, invisibly birthing all particles and forces alike. Let us now descend into that hidden terrain, to the very fabric beneath Reality. Section 5. Quantum fields. The fabric beneath reality. We are taught to think of particles as points, tiny indivisible grains making up everything. But this is an illusion. There are no solid beads beneath the surface of things. There are only ripples, waves, and invisible oceans. We are taught to think of particles as points, tiny indivisible grains making up everything. But this is an illusion. There are no solid beads beneath the surface of things. There are only ripples, waves, and invisible oceans. Everywhere in the universe, even in perfect vacuum, unseen quantum fields spread. Vast, eternal, vibrating. Electrons? They are just localized disturbances in the electron field. Photons? Ripples in the electromagnetic field. All particles, all forces, every glimmer of substance, they are excitations, like the pluck of a string echoing across a limitless, invisible sea. This is not metaphor. It is the architecture of reality. The universe is not made of things. It is made of fields, and particles are how those fields speak. A scientific fact. According to the standard model of particle physics, each type of particle corresponds to a quantum field that permeates all of space. These fields interact, exchange energy, and give rise to everything from the sun's light to the chemistry of your breath. But one field stands apart, mysterious, massive, and slow to reveal itself: the Higgs field. Unlike others, the Higgs does not just ripple, it sticks. It clings to particles as they move, granting them inertia, which we perceive as mass. Without it, quarks would be massless, atoms would not hold, stars could not burn, life would not form. It is a gentle resistance to movement, and from that resistance, matter becomes real. In 2012, at CERN's Large Hadron Collider, the Higgs boson, the long-predicted ripple of this field was finally detected, a whisper in the noise of collision, a signal that the field was truly there, woven into the vacuum beneath our feet. And yet, the Higgs raises more questions than it answers. Why is its value what it is? A tiny change in the strength of the Higgs field would render the universe unrecognizable, too unstable, or too still to form stars or atoms. Physicists call this the hierarchy problem. Why is the Higgs field's energy so low compared to other forces? What protects it? What balances it on such a fine edge? Some theories suggest that unseen supersymmetric particles counterbalance the quantum effects that should make the Higgs unstable. Others imagine a multiverse, an infinite landscape of possible universes, each with different field values, and we just happen to be in one where life is possible. And still deeper, stranger ideas await. Some physicists now believe that space and time themselves may not be fundamental, that fields, particles, and even the geometry of the cosmos might emerge from something deeper, entanglement, perhaps, or a network of quantum information flickering beneath space-time like code beneath a screen. In this view, fields are not the end. They are the surface of something else, an interface, a veil. Imagine for a moment that the most powerful force in the universe is not gravity, not fusion, not dark energy, but the quiet hum of something foundational, a symphony of fields vibrating just so, giving rise to form, force, and fire. Even in the coldest vacuum, these fields never truly rest. They fluctuate, endlessly, randomly, birthing pairs of virtual particles that flicker in and out of existence. This seething nothing is not truly nothing. It is alive with potential. It is from this seething void that matter may arise. And it is in this void that another form of power waits, a mirror to the matter we know, identical in mass, opposite in charge, a spark that, when touched, annihilates everything it meets. We now turn to antimatter. Picture a mirror. Now picture reality reflected within it, identical, yet inverted. This is antimatter, the symmetrical twin of the material world. For every particle you know, electron, proton, neutron, there exists an opposite, positron, antiproton, antineutron, same mass, opposite charge, same spin, a cosmic echo. But when matter and antimatter meet, the symmetry shatters. They vanish in a burst of pure energy, an event so efficient, so total, that it defies comparison. No ash, no fragments, just light, radiation, release. A scientific fact. The annihilation of a single gram of matter with a single gram of antimatter would produce around 1.814 joules of energy, enough to power a major city for days or obliterate it in an instant. This is Einstein's equation, E = mc2, expressed in its most dramatic form, the conversion of mass to energy, nothing wasted. And yet, this tremendous power is nearly absent from our universe. For reasons unknown, the cosmos is almost entirely matter. Antimatter should have formed in equal quantities during the Big Bang. Every theory, every model, every law we know insists on this balance. And yet, here we are. Planets, stars, galaxies, all made of matter. The antimatter is simply gone. This is the baryon asymmetry problem, one of the great unsolved riddles in physics. What tilted the scales? Did some subtle asymmetry in the early universe allow matter to survive just slightly more than antimatter? Were there unknown particles, unknown forces that nudged the outcome? Some experiments, like those at CERN, search for violations of CP symmetry, the law that matter and antimatter should behave identically under inversion. If even a tiny difference exists, it could explain why anything exists at all. But the results are murky, promising, incomplete. Speculative theories abound. Some suggest that antimatter wasn't destroyed, only sought, irradiated, that vast regions of the cosmos may be composed of anti-stars, anti-planets, anti-galaxies, exiled beyond our view, divided from us by distances so vast we cannot yet see the annihilation boundary. Others go deeper still, imagining mirror universes, where time runs backward or where antimatter forms the dominant reality, and our universe is the strange absence. Yet even here, in our matter-dominated world, antimatter is not entirely gone. It flickers in thunderstorms. It emerges in radioactive decay. It is manufactured fleetingly in particle accelerators and certain kinds of nuclear reactors. It even arises in the brain. Positrons are emitted during PET scans, allowing us to image thought with particles from annihilation. And in space, nature does what we struggle to. In the heart of neutron stars and magnetars, antimatter may churn in violent collisions. In high-energy jets from black holes, particles and antiparticles are born in a spray of plasma and light. Still, harnessing it is no small feat. To store antimatter is to trap lightning made of ghosts. It must be held in magnetic vacuums, never touching the walls, never brushing against normal matter. The slightest breach and the energy is unleashed. Yet even with our crude tools, we've done it. We've created antihydrogen, an atom made of a positron and an antiproton, and held it in magnetic fields for precious milliseconds, a whisper of the mirror world floating above a lab floor. And the dream remains. Could antimatter become a power source, a propulsion system, a weapon, a star in a bottle? But even dreams have limits. Antimatter is incredibly costly to produce, billions of dollars for mere nanograms. Until a new method is discovered, it remains a curiosity, a promise, a force we can touch but not yet command. Still, in its annihilation lies a lesson that the universe is capable of total transformation. That power can be both creative and absolute, and that behind opposites there may be deeper unities. But there are places where even matter and antimatter fall silent, where the struggle is not between opposites, but between fields of unimaginable tension. Magnetic force wound 1 trillion times stronger than Earth's own, a tension so vast it warps atoms, rips space, and turns dead stars into weapons. We now approach the most magnetic monsters in the cosmos, Magnetars. In the deep graveyards of stellar death, a rare and terrifying relic sometimes forms, not quite a star, not yet a black hole, but something far stranger, a magnetar. Born from the collapsed core of a massive star, a magnetar is a kind of neutron star, already one of the densest objects in existence. Picture a mass greater than our sun compressed into a sphere just 20 kilometers wide, a city-sized titan. But while all neutron stars are dense, magnetars add something else, magnetic fields so powerful they defy comprehension. A scientific fact: a typical refrigerator magnet has a strength of about 0.01 teslas. Earth's magnetic field, roughly 50 microteslas. A hospital MRI, about 1 to 3 teslas. A magnetar's magnetic field can exceed 10 to 11 teslas. That's 1,000 trillion times stronger than Earth's. So strong it can distort atomic orbitals, crushing the shapes of atoms. So intense it can strip electrons from atoms at a distance of hundreds or even thousands of kilometers. The magnetic pressure near a magnetar is so immense it can rupture the quantum vacuum itself, spawning particle-antiparticle pairs from empty space. This is not fiction. It is not metaphor. It is power incarnate. These monsters spin, too, sometimes hundreds of times per second, spraying radiation into the cosmos like a strobe of cosmic fury. When a magnetar's crust fractures, and yes, even something this dense has a crust, it causes a starquake. The quake releases an enormous burst of gamma rays, energy so intense it can overwhelm satellites orbiting Earth, even from tens of thousands of light years away. On December 27, 2004, such a burst arrived from SGR 180620, a magnetar located 50,000 light-years from Earth. In just 0.2 seconds, it released more energy than the Sun does in 250,000 years. For that brief moment, it was the brightest event ever recorded from beyond the solar system. And it came from something no larger than Manhattan. Yet magnetars are rare. Of the billions of stars in our galaxy, only a few dozen magnetar candidates have been found. They live fast, burn out quickly. Their fields decay in mere thousands of years, a flicker on cosmic scales. Why do some neutron stars become magnetars while others remain normal? That question remains open. Some believe the progenitor star must have rotated extremely rapidly during collapse, twisting magnetic field lines into tighter, deadlier knots. Others suggest exotic states of matter inside, like superfluid neutrons or even quark matter, that enable more efficient magnetic field amplification. But the truth is uncertain. We do not know which stars will leave behind these ticking bombs of magnetism. Speculation runs wild in the theoretical corridors. Could magnetars be responsible for the mysterious fast radio bursts, ultra-short, ultra-bright signals that last milliseconds and originate from distant galaxies? Some think yes. Their sudden, violent outbursts fit the bill. But definitive proof remains elusive. There are whispers, too, of their role in the early universe. That primordial magnetars, born in denser, faster times, could have shaped galaxies with their fields, seeding cosmic magnetism on a vast scale. That even now their ghosts might be tugging on the structure of space. Yet for all their might, magnetars eventually quiet. Their fields decay, their outbursts subside. They cool into silent neutron stars, dense, dull, arc, ancient. The fire fades. The fury passes. But the lesson remains, that magnetism, often overlooked, can rise to monstrous scale. That a force we barely feel on Earth can become an engine of chaos among the stars. And it points to a stranger truth. Even nothingness is not immune. The vacuum itself, that which we consider empty, is alive with tension, seething, trembling, unpredictable. It hides a power that needs no particles, no mass, no matter. The next chapter awaits in that emptiness, where vacuum energy breathes power into the void. Imagine the purest emptiness you can conceive. No stars, no dust, no particles, not even the echo of a forgotten photon, just nothing. But this nothing is a lie. In quantum physics, there is no such thing as a truly empty vacuum. Even when all observable energy is removed, the vacuum still hums. It trembles with possibility. Virtual particles flicker into and out of existence, borrowing energy from uncertainty, annihilating before they can be caught. Space is not a passive stage upon which reality plays. It is an active fabric, a field in tension. This restless nothingness carries a name: vacuum energy. A scientific fact: even the most perfect vacuum has a non-zero baseline energy, a floor that can never be reduced to zero. This energy arises from the uncertainty principle itself, the idea that position and momentum, or energy and time, can never both be precisely known. This uncertainty ripples into existence as quantum fluctuations, a spontaneous dance of creation and erasure. The consequence is staggering. The vacuum, what we once thought of as nothing, may contain more energy than all the stars combined. This vacuum energy may be the true identity of dark energy, the invisible force accelerating the expansion of the universe. If true, it means the future is written not in matter or heat or light, but in the energy of the void. And yet artis. Iori's conflict. Quantum field theory, when applied to vacuum energy, predicts an energy density that is 120 orders of magnitude too high, a number so large it breaks all physical sense. The cosmological constant problem is the worst theoretical mismatch in the history of science. Something, some balancing act or hidden mechanism, must be at work, subtracting, canceling, stabilizing, we do not know what. Still, there are strange confirmations of vacuum power. The Casimir effect, for example. Place two uncharged metal plates a tiny distance apart in a vacuum, and they will attract each other, not because of static or gravity, but because the vacuum energy between them is slightly lower than the vacuum energy outside. The plates are literally pushed together by nothing. And in space, perhaps this nothingness played the ultimate role. At the birth of the universe, an epoch known as cosmic inflation is believed to have occurred, a moment of wild, exponential expansion, driven by vacuum energy far greater than what exists today. Space inflated faster than the speed of light, smoothing the universe, planting the seeds of galaxies, and then suddenly this false vacuum decayed, releasing energy, forming matter, birthing time. We are here because the vacuum changed its mind. But is vacuum energy stable now? Will it stay constant forever? Or is our universe perched in a false minimum destined to fall again, to decay into a deeper vacuum, one with different laws where matter cannot exist? This is the unsettling speculation behind the idea of vacuum decay. In this scenario, a quantum fluctuation could cause a bubble of lower energy vacuum to form. This bubble would expand at the speed of light, rewriting physics in its wake. We would not see it coming. We would not feel it. One moment, everything would exist. The next, it would not. And still, we dream of harnessing those. In science fiction and theory alike, vacuum energy tempts us with infinite fuel, a zero-point energy engine that draws power from the background hum of space itself. No moving parts, no fuel tanks, just vibration, possibility, tension. But even the smallest attempt to grasp this power confronts the unknown. Can we control the structure of the vacuum? Can we shape its fluctuation? Or would such attempts unravel the stage itself, tearing the fabric of what we call real? In the cold of interstellar space, far from any star, vacuum energy still sings. It is soft, but it is everywhere, and its quiet persistence may outlast everything else. Yet energy alone does not shape the cosmos. There is something subtler, something woven into the rules themselves. Information, not a thing, but a relation, a pattern, a code. What if the most powerful force in the universe is not a field or a bang, but a bit? We now move into the strange domain where physics, computation, and consciousness converge to explore the power of information itself. It doesn't weigh anything. You can't touch it, hold it, or burn it. But in the deep logic of the universe, information may be more fundamental than matter or energy, the true coin of reality. A simple bit, a 1 or a 0, can describe anything, from the spin of an electron to the shape of a black hole, and increasingly, physicists are beginning to suspect that these bits are not just descriptions of the universe, but the building blocks of it. Information, in this view, is not abstract. It is real, physical, indestructible. A scientific fact, in 1961, Rolf Landauer showed that erasing one bit of information, truly erasing it, requires a release of energy, proportional to temperature. This links information to thermodynamics, tying logic to heat. Computing, thinking, remembering, they all come with a physical cost. But the story grows stree, anger near the edges of knowledge. When matter falls into a black hole, what happens to the information it contains? Its quantum states, its entangled relationships, its internal structure? Are they erased forever? Hawking's calculations once said yes. Black holes evaporate through Hawking radiation, emitting random particles until nothing is left. But this led to a disaster in physics, the information paradox. Because quantum mechanics demands that information is never lost, the wave function, the most sacred object in quantum theory, evolves predictably. It may blur, but it never deletes. The apparent destruction of information at the black hole's heart would break the rules, not just of theory, but of reality itself. So a great debate was born. Today, many physicists believe the information does survive, encoded somehow in the radiation or smeared across the event horizon. This is the essence of the holographic principle, the idea that everything inside a volume of space can be described by information written on its surface, like a hologram, where a 3D image emerges from a 2D plane. The math behind this is startling. In string theory, the ADS-CFT correspondence suggests that a universe with gravity can be exactly described by a different universe on its boundary without gravity at all. Everything you are, every thought, every atom, may be a projection from information stored on a cosmic screen. This is not metaphor. It is one of the most rigorously tested concepts in modern theoretical physics. The universe, it seems, may be informational at its core. But what is information? It is not energy, but it takes energy to change. It is not matter, but it can describe every configuration of matter. It can exist in DNA, in sound, in light, in memory. It can survive in photons crossing galaxies or in the spin states of atoms frozen near absolute zero. And perhaps it lives in the laws themselves. There is growing speculation that the laws of physics are themselves information structures, emergent rules flowing from deeper computational patterns, that the universe may, at its lowest level, function not like a machine, but like a quantum computer. In this vision, particles are data, forces are logic gates, time is computation. Reality is the result of a vast, unceasing calculation. Some call this digital physics, others pan-computationalism, the idea that the universe computes its own evolution, bit by bit. If true, then information isn't just powerful, it's everything. And the implications ripple outward. If black holes store information, they may be hard drives of the cosmos, preserving the data of everything they consume. If particles are informational events, then physics may be programmable. If the brain is an information processor, electric, chemical, symbolic, then perhaps consciousness too can be reduced to code, but this opens doors that are hard to close. Could a being, natural or artificial, decode the universe at this level? Could we edit the laws themselves, like rewriting lines of cosmic software? Could civilizations transmit not just messages, but selves encoded into streams of quantum bits spreading across space as patterns of pure thought? These ideas teeter on the edge of science and philosophy, yet they emerge from solid mathematics, from real physics, from the tension between what we know and what we dream. And perhaps it is here, not in fire or fusion, but in form, that true power hides. For even the greatest energies fade, stars burn out, matter decays, but information, if preserved, can last. It can move, it can replicate, it can shape minds, tools, galaxies. And now we turn inward, to the most complex informational structure we know. Not a nebula, not a quasar, but you, the human mind, the storm of thought, the power of perception. Amid all the great forces, fusion, gravity, magnetism, vacuum, there exists a quiet anomaly. It weighs little, it radiates no light, it bends, no space-time, and yet it beholds everything. Consciousness. Of all the known structures in the universe, the human brain is the most complex. A 3-pound lattice of neurons and glial cells, coursing with chemical signals and electrical storms, sculpted by evolution and lit from within by awareness. Roughly 86 billion neurons, each forming thousands of synaptic connections, exchanging ions and information in patterns still not fully understood. But the mystery is not just how it works. It's what it does. The brain does not merely process, it experiences, it dreams, doubts, imagines, loves. Somehow, within its wet circuits, the cold equations of the cosmos gain a witness, and in that witnessing, something powerful happens. Consciousness turns information into meaning. A scientific fact: brain activity consumes about 20% of the body's energy, despite its small size. This metabolic cost fuels a constant stream of activity, from sensory input to abstract thought, from memory consolidation during sleep to the anticipation of future events. The brain is not passive, it is predictive, it simulates, it constructs models of the world and of itself. Yet, science cannot fully explain what consciousness is. It can trace correlates. Brain regions that light up during awareness, neural rhythms tied to focus or dreams. But the hard problem of consciousness remains unsolved. How do electrochemical signals become subjective experience? Why does red look red? Why does music move us? Why does a thought feel like anything at all? Some theories, like integrated information theory, suggest that consciousness arises from a system's capacity to integrate information. That awareness is what it feels like when information is bound into a unified whole. Others, like orchestrated objective reduction, delve into quantum realms, proposing that consciousness is tied to quantum processes in microtubules within neurons. Still others turn to emergence. The idea that complexity gives rise to new properties, irreducible to the parts. That thought is to neuron what wetness is to water, real, but dependent on collective behavior. Yet these answers remain speculative. The essence of awareness eludes capture, and perhaps that is part of its power. For consciousness does what no force field can. It asks why. It reflects. It chooses. It imagines futures that have not yet occurred. It grieves for those who have passed. It creates tools, builds stories, alters environments, manipulates matter not through mass or motion, but through intention. This is no small thing. Human thought has reshaped landscapes, redirected rivers, engineered artificial stars within reactors. It has mapped the genome, peered into atoms, and charted galaxies billions of light years away. A conscious mind, equipped with science and time, can rival the output of stars. And in recent years, consciousness has turned outward, onto itself. We have built machines that learn, neural networks that mimic the patterns of our minds, systems that write, speak, adapt. Are they conscious? Most say no, not yet. But the line between tool and self grows blurrier. Some believe that consciousness is not limited to biology, that one day artificial minds may awaken, their awareness arising not from neurons, but from silicon and code, that one day thought may transcend its carbon roots. Others speculate about panpsychism, the idea that consciousness is a fundamental property of the universe like mass or charge, that awareness may not emerge from complexity but may pervade all things in degrees. But even if we are alone in our kind of awareness, for now, it is enough. For within us lies the ability to understand, not just to observe, but to model, to remember, to predict, to connect. Through language, we transmit knowledge across time. Through mathematics, we glimpse truths beyond our senses. Through imagination, we reach for what has never been. No other known structure in the universe, not a quasar, not a pulsar, not a black hole, can do what a mind does in a quiet moment, look inward and ponder its place in the whole. Power in its subtlest form may be awareness itself. And yet, we are not just minds, we are bodies, and the body too holds power, in chemistry, in memory, in evolution. For the most enduring power of all may not be a force or a field, but life. And so now we turn to the miracle that endures across ages and stars, the force that replicates, adapts, survives biological life. From stardust and chaos, from carbon and time, a spark once kindled on a pale blue world, and the universe changed. Life is not a force in the traditional sense. It does not curve space-time or generate magnetic fields, but it replicates, adapts, and remembers. And in that persistence lies a kind of power no star or particle has ever known. The power to endure, to evolve, to transform itself across epochs. A single strand of DNA, no wider than 1,000th of a hair, contains a 4-letter alphabet, a code, and from this code, life builds all it needs: membranes, muscles, eyes, thoughts. Each living cell is a molecular city, a churning, self-repairing, semi-autonomous machine, encoded by history and refined by necessity. A scientific fact: every human cell, from bone to brain, carries about 3 billion base pairs of DNA, the molecular legacy of billions of years of evolution. And yet, the information needed to describe the entire biosphere, every species, every relationship, is far greater. Life is not just a molecule. It is a network, a feedback loop of genes and environments dancing across deep time, from the simplest microbe clinging to a thermal vent to the redwoods rising toward sunlight to mycelium that gaze at stars. Life expresses itself in endless forms, always reaching, always adjusting. But life's true miracle is not its complexity. It is its persistence. Through 5 mass extinctions, supervolcanoes, asteroid impacts, and the shifting crust of continents, life has not vanished. It rewrites itself, discards what fails, amplifies what works. Evolution is not progress. It is endurance, not perfection, but plasticity. And in its resilience, life begins to bend the universe back upon itself. Some microbes thrive in boiling acid, others in frozen deserts, others in nuclear reactors. Extremophiles that expand our notion of what life can be. Could similar organisms thrive on Europa, or Titan, or beneath the sands of Mars? If they exist, they too would be powered by the same logic: replication, mutation, selection. There may be life elsewhere in the cosmos, countless times over. Or perhaps life is rare, a fluke, a chemical accident so precise and improbable that it occurred only once, here. But even if we are alone, we are still an expression of something ancient. Every cell in your body traces back to Luca, the last universal common ancestor, a single living system billions of years ago from which all earthly life descends. You are not apart from the tree of life. You are its latest bloom, and with life comes awareness, and with awareness comes choice. This is life's unique gift, the ability not just to respond to the environment, but to change it, to shape stone into tools, to make fire, to plant seeds, to launch satellites. No supernova has ever written a poem. No neutron star has ever asked why it burns. Only life, fragile and soft, dreams. Some speculate life is not merely a product of the universe, but its goal, that through life, the universe awakens to itself, that consciousness is the cosmos looking in a mirror, seeing not fire and fusion, but thought and time and longing. Others imagine that life is information's answer to entropy, a structure that resists decay, that builds pockets of order in a sea of increasing disorder. We live in defiance of thermodynamics, not breaking its laws, but surfing its gradients, extracting energy to build patterns that would otherwise not form. And yet, we die. Life's power lies in its transience too. No organism is eternal, but the pattern survives. The genes pass on, the memories ripple outward, the culture persists. One cell becomes 2, one idea becomes many, one species gives rise to thousands. And now, in this moment, life reaches again, not with claws or roots, but with circuits, rockets, radio waves. We are extending life beyond its biology, synthetic biology, artificial intelligence, space colonization. If life survives long enough, it may spread between stars, not by crawling, but by encoding. Beams of data, self-replicating probes, seeds of consciousness riding light itself. The cosmos may one day be full of life, not born of Earth, but descended from it. And perhaps this slow, improbable blooming, is the most powerful force in the universe. Not brute strength, not instant annihilation, but the quiet, tenacious will to exist, to adapt, to know. And now only one frontier remains, the singularity of force, time, and space, the place where everything ends and something else begins. We now fall toward the final crucible, the black hole. In the beginning, there is light. In the end, there is gravity. Black holes are not objects, they are regions, boundaries where space bends so steeply that nothing can escape, not even light. They are not stars, they are endpoints, the punctuation marks of cosmic sentences. A black hole forms when matter collapses beyond a critical limit, when even atomic pressure, neutron repulsion, quantum resistance cannot hold back the crush. Mass folds in upon itself, shrinking not just physically but geometrically, until all known dimensions give way. The result is a singularity, a place of infinite density, wrapped in a cloak of invisibility known as the event horizon. A scientific fact: at the heart of a black hole, our known laws break. General relativity, which governs gravity, predicts infinite curvature. Quantum mechanics, which rules the small, refuses this. The theories do not agree. Somewhere inside that darkness, our understanding fails. But the edge, the event horizon, speaks to us. Black holes are not black. They radiate. In 1974, Stephen Hawking showed that quantum effects near the event horizon cause particle pairs to emerge. One falls in, the other escapes. Over unimaginable timescales, black holes evaporate, losing mass, dying, the coldest furnaces in the cosmos, burning information instead of fire. But what happens to what falls in? This is the great paradox. If information truly disappears into a black hole, never to return, then unitarity is violated and the bedrock of quantum mechanics is cracked. Yet if it does return, how? Encoded in Hawking radiation, smeared on the event horizon, trapped in a baby universe? No one knows for sure, and yet we keep learning. In April 2019, humanity beheld its first real image of a black hole, not with eyes, but with algorithmic synthesis. The Event Horizon Telescope, a planet-sized array of radio dishes, captured the silhouette of M87's central black hole, a dark disk wreathed in fire, 40 billion kilometers across, devouring space at the center of a galaxy 55 million light-years away. But not all black holes are giants. Some are born from dying stars, stellar mass remnants that drift in darkness, merging quietly until gravity shouts again. In 2015, the LIGO detectors recorded the first gravitational waves, ripples in spacetime itself, from two colliding black holes. The signal lasted a fraction of a second, but it carried the energy of 3 suns converted into waves. We had heard the universe not with light, but with vibration, the first tremors of the cosmic sea. And stranger things await. Some black holes may spin so fast they drag space-time into spirals. Some may be gateways to wormholes, hypothetical bridges to other regions of the universe, or other universes entirely. Some may sit at the centers of galaxies, shaping their arms, their stars, their histories. Even time behaves differently here. Near a black hole, time slows. Clocks tick slower. Light stretches redder. To fall toward one is not just to approach a point. It is to fall through time itself. This is not poetic license. This is measured fact. And yet, black holes may be holographic libraries, preserving every detail of everything that fell into them, inscribed somehow on their horizons. Not deleted, not lost, just hidden, waiting to be decoded. Perhaps they are not endings. Perhaps they are mirrors. Perhaps the most powerful thing in the universe is not any one of these forces, not gravity, not entropy, not light, not magnetism, but what happens when they all converge. In the heart of a black hole, everything we know dissolves. Particles, time, causality, even space, all distinctions blur. What remains? Maybe nothing. Maybe everything. Maybe a blueprint, a seed, a silence that holds the potential for new beginnings. Because after the burning of stars, after the unfolding of fields and minds and matter, after the last black hole evaporates into quantum whispers, something will remain. Possibility. The possibility that the universe begins again, that the vacuum shifts, that new laws emerge, that from nothing, a new Big Bang cracks the silence. And when it does, power will awaken once more. Not as a blast, but as a breath. Let us return now to that breath, to earth, to your body lying still, to your chest rising and falling in the quiet, The same atoms that once danced in stars now spiral in your blood. The same laws that carve black holes shape your thoughts. The same silence that fills the void surrounds you now. Close your eyes. Feel the pulse of existence echoing in the dark. From the deepest cores of neutron stars to the whisper of a sleeping mind, power takes many forms. But the greatest of them all may be this: to witness, to wonder, to rest.